In this problem, we are given the following op amp in a circuit diagram. We need to calculate V1, V0, I2, and I0. So when we look at this, there's a few things that we should note before we even calculate this. First, we have our negative terminal right here, and then a positive one right here. And we know that our positive terminal is non-inverting, and then our negative terminal is inverting. You can think non-inverting is positive and invert, because when you invert something, it's negative. So inverting and non-inverting. So this is the inverting amplifier. So this diagram is of an inverting amplifier circuit. When we look at this, the closest thing to our left side, because I like to look from left to right, is this I2 right here. So we can solve for that. This is going to be pretty easy because we have a voltage here and a resistance here. And we know by Ohm's law, voltage over resistance is current. And we know that this current that'll be from this voltage and this resistor are only going to go to our I2 because no current ever enters our op amp. So no current's going to go through here. That means all current has to go out of there. So that means when we solve that, we're going to say that our I2 is equal to the 150 millivolts over the 2 kilo ohm resistor. So we need to get rid of the milli and kilo. That way we only have volts over ohms, and that'll give us amps. So if we look in the notes I have linked below in the description, in section I think 1.2, late 1.2, we can see all the conversions. We're going to have 1k over 10 cubed. That's the conversion for kilo. And then for milli, we're going to have 1m over 10 negative cubed. If we do this, we're going to get that our I2 is equal to 7.5 times 10 to the negative 5. This is in amps. Our answer for I2 is asking for us in microamps. So we're going to have to convert this. Looking at the same table, we know that 1 micro is equal to 10 to the negative 6th. So when we multiply this by a 10 to the 6th, or divide it by 10 to the negative 6, we're going to get that our I2 is equal to 75 milliamps. And that is our answer for this part. Next, we're going to look at this V1 right here. Well, we're going to do the same thing kind of that we did to find our I2. When we were looking at our I2, we had this 150 millivolt voltage here, and we had this 2 kilo ohm resistor. And then we used it to find our I2 like this. Well, now we have an I2, and then we have a 40 kilo ohm resistor. And then we're going to use both of these to find our V1. We know that V1, or any voltage, is equal to current times resistance. So we can say that this is equal to our I2 times resistance. And we know our I2 to be 7.5 times 10 to the negative 5 amps. And then we know our resistance to be 40 kilo ohms. We have to convert this to ohms. We already know the conversion. We can look up here. So this is going to basically be, if we get rid of the k, times 10 to the cubed. If we do this, we're going to get that our V1 is equal to 3. That's almost the answer. However, we should note that when we look at a circuit like this, from our v-naught, this is the output of our op amp. If it's connected like this, we're going to get some negative feedback from our v-naught. What that means is that some of the voltage is going to be going this way, back down, this way, and kind of back into our op amp. And when it's going this way, it's going to be going in this direction, over the 40 kilo ohm resistor, over the V1. And we can see that this voltage is going to be going in the opposite direction of our current. And we know that if voltage is going in the opposite direction of our current, we're going to have a minus. So the actual answer is going to be V1 is equal to a negative 3. And the units for this is going to be in voltage because we have amps times ohms. So this is the answer for our V1. Now, the next thing I want to solve for is v-naught. That looks like something good to solve for. And to solve for our v-naught, what we are going to do is look at this node right here. So we're going to be looking at this node And we know that coming into it is going to be our v-naught this way because of the negative feedback. We know that our v1, because into the positive out of the negative, will be going down this way. And we know that the voltage will be going over this way as well. So when we write this, we are going to say that we have a v1 over 20 kilo ohms. I'm going to do that first. Now I'm going to have a plus, and then we know that we have our v1 over the 40 kilo ohms. And then coming into this, we are going to start with our v1 as always, and this is happening over the 50 kilo ohms. So this is going to be over 50 kilo ohms, and when we look what's coming into it, we can see that it's going to be our v-naught. So we'll have a minus v-naught, and at a node, it's all going to be equal to 0. This is our current equation. I'm going to multiply the entire thing by a 10 kilo ohms. That way we can get rid of our 0 and then the kilo ohms for the denominator. And now I'm going to combine like terms. So I'm going to have a v1, and then in our parenthesis 1 over 2 plus 1 over 4 plus 1 over 5, and this is going to be closed off like this. Now we are going to have a minus v-naught over 5, but we can put that on the right side as a v-naught over 5. So this is going to be our current equation. Now I can plug all this into a calculator and substitute for our v1 a minus 3. So we're going to get 0.95 for our left side. Since we want to solve for v-naught, we have to get that by itself. We're going to multiply both sides by 5 to get v-naught by itself. And if we do that, we're going to get a negative 14.25. And this is the answer for our v-naught. Lastly, we're going to be looking at our I-naught. So for our I-naught, we know it is coming out this way. We have a node right here, so we can use this node. Since it's going out of our node, it's going to be a positive I-naught. We have this v-naught here. However, we are going into the positive, out of a negative with voltage, so it's going away from this node. So from here, we're also going to have a plus v-naught over 25 kilo ohms. And then from our negative feedback, this current right here, we can see that our voltage or our current will be going out of this node. So since it's going out of this node, this will be a plus v-naught minus a v1, and this is happening over the 50 kilo ohm resistor right here. And at a node, it's all set equal to 0. We want to find I-naught, so we're just going to move everything over to the left side. So we're going to have a negative v-naught over 25 kilo ohms, and then since we're going to have a plus out here, we're going to switch the signs for our numerator and do a v1 minus v-naught, and that's over the 50 kilo ohm resistor. Now we can plug some things in. We know what our v-naught is going to be. It's this negative 14.25, and we know what our v1 is. It's this negative 3 volts. And we know that for a K, it's equal to 1,000. So we should keep that in mind when we plug this in here. If we do that, we are going to get 0.000795. I'm going to rewrite this as 795 times 10 to the negative 6. And since we're solving for I, this is going to be in amps. We know that our I-naught is asking for it in microamps, so we're going to do the same conversion we did earlier. We know that 1 micro is over 10 to the negative 6th. And then if we do that, we can actually just see that the 10 to the negative 6 and the 10 to the negative 6 are going to cancel out. So we get 795 microamps, and that's equal to our I-naught. So that's the last part of this problem. If you want more problems like this, you can look in the description for a playlist below. That's all introduction to circuit analysis, as well as notes that cover the entire course of intro to circuit analysis.